Okay, so we've gone over every concept that we're supposed to go through except circular motion and drag force. So, before we reach those two last topics, really the most important one is circular motion. Drag force, I'm just going to spend 5 minutes. You should have seen it in the lectures already, so I just wanted to clarify conceptually what it is. But before we start, any questions based on what we've done? As you have redone all those problems on your own, check the archives, recheck the collaborate if needed, read the corresponding book section if needed. Is everything okay, or is there any question on your learning journey that may have occurred on Newton's chapter? Either with respect to the method or friction, pulleys, equilibrium. Pulleys 5, okay. Pulleys in general. Oh, okay. Oh, what is that subface? Pulleys are cool, they're easy. No? So that means I didn't do a good job. Okay, let's redo that together. Oh, P5, sorry. Okay. I should have a nice little screenshot of that guy. Yeah. Okay. Excellent question. Good. So let's do one example by considering the mass. Let's make it big. Okay, what is the question? What do they want? They give us M1 and they want M2 in terms of M1. Okay. So if we consider massive pulley, we have to consider the same mass for all pulleys. Okay. Okay, so they want M1, no, they want M2. So let's start with the object that has M2. Naturally. Let me make it bigger so we can put the free body diagram directly on our system. Okay, so if we consider, so I should be able to reproduce what you've done, Jamie, but with just one more force. So this is what I'm going to call M2G. You should have the same, and let's call this T1. So far so good. Do we have the same so far? Okay. So M2 will give us the following equation. I'm going to skip the coordinate system at this point. It's so trivial. T1 is equal to M2G. Alright. Perfect. Enable perfect tense. Now, next one. Obviously, let's go to pulley B, since it's in contact with M2. Newton's third law tells us this is T1. We follow the string. This is T1. Let's follow the string all the way, because we may need pulley C. T1, T1. Okay. Then, of course, this pulley now has mass, so let's call it W. And then we have another force, I don't know what it is, let's call it T2. Okay, so the difference between massive pulley and massless pulley is I have an additional force, which is the weight of the pulley, which has the same characteristic as the weight in general. It goes down. So object B will give me T2 is equal to 2T1, but then I had to add that extra weight. Well, if you were dealing with massless pulley, that W term should not be there. Okay. Since C is connected to M1, let's try jump to C and see if we can get away with it. If we can avoid doing pulley 8, that would be good. C2 has one more force here, but this one I recognize as I follow the string. It's the same as T2, because T2 is here, and T2 is here. T2 Newton's third law and the property of the pulley. Oops, that should be a 2. So now T2 is here, Of course, I have another one here called T3, and the weight, same weight as pulley B. So now I'm going to have 1T2 plus 2T1, and this is equal to T3. And again, the only new thing here is that extra W. Alright. Now let's do the last. Obviously this is T3 by Newton's third law, and this is M1G. So M1 will give us the last equation, M1G is equal to T3. Alright, now all we have to do, so the new thing with massive pulley is obviously those two terms right here. So let's substitute T3 here and T1 here. So we're going to have from B, T2 is equal to 2M2G plus W. Question from Mossman. For B, is the line next to T1 supposed to be a G? For B, so you're looking at the free body diagram? Or the equation? Oh, the equation. T2 is equal to 2T1 plus W. Why do you want G? Oh, my bad. Yes, this W is mass of the pulley times G. Yes, yes, yes. So I could have written it as, thank you, that W that I wrote is defined as mass of the pulley times G. So either or. Thank you, thank you. And we would have to use that anyway, because they want us to express the answer in terms of little g. But we can do that at the end. So you can either represent it now or do it at the end. Thank you, thank you, thank you. And then equation C, T2 is equal to T3, which is M1G minus 2T1 plus W. I move the 2T1 on the other side, and I can replace it right away by 2M2G. Yes, thing. Yep, yep, yep. Common mass of MP is equal to 2 kilograms. Therefore, the W is the same. And now I can minus those two equations. So I have 0 is equal to 2M2G plus W minus M1G minus 2M2G plus 2M2G minus W. And I'm solving for M2. So M2 will be, hey, look at that! So obviously in this case, the result is the same. M2 is exactly the same with massive or massless pulley because the W disappears. What a beauty. So we have M1G divided by 4. Is that what you had, Jamie? And that's why you were wondering? What was that devilry? You know, it wasn't planned. Usually it stays somewhere, somehow. I guess in this case. Okay. Does that clarify? You treat the weight as any other weight, vertically down. So you just add it to your free body diagram. Okay. So let me put in red what is new from, you're welcome, from massless. This is new from massless. This will be new. This will be new. This will be new. 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 So those are the new stuff if you consider massive pulley. And again, in this case, they happen to cancel each other, which is interesting. In all the other problems, I believe that they won't. Good. Good question. Anything else? On your homework, yes, can you be more specific? What homework are you referring to? Yes, circular motion is what we're going to go towards to. CM1, okay. Let me wait a little bit just to make sure there is no question in other topic. No. W is the weight of the pulley. Remember, the weight in the free diagram can only be the weight of the system. So this weight must be the weight of this pulley. This weight must be the weight of this pulley. M2G is the weight of this mass. M1G is the weight of this mass. W is here defined like this: the mass of the pulley times G. Okay? If W is no good, define it as WP to remind yourself, okay, this is the weight of the pulley. Does G not cancel? Oh, you're right. Otherwise, units don't work out. Thank you. So the G canceled too. Even easier. Thank you. Oh, so I should rephrase the problem. Thank you. Let me rewrite it so that the G can be taken out, so it's not confusing. That was P5. Awesome. Thank you, Kay. Anything else before we get to circular motion and investigate that CM1? And then bank curve. F6. Didn't we do F6 yesterday? Wait, Monday? Or am I going crazy? I mean, F6 or F7? I think we did F6, no? Do we need to redo it? Oh, sorry. F8. F5. Yes, we did F5. But I'm pretty sure we did F6. We must have done that with friction. That kind of ring a bell. So F8. Equilibrium with friction. Excellent problem. Okay. Where are you? Right here. So there's two parts to this problem, A and B. First, we know the weight of A. So remember, do not mix up your weight and your mass. Sometimes they give the weight, sometimes they give the mass. The weight is, by definition, the mass times gravity, two different things. The mass is defined in chemistry as the amount of matter, amount of atoms. In physics, I won't give you a definition because we have no idea. But the weight may change depending on the value of G. For us, we've seen that the value of G on the surface of the Earth is 9.81. But obviously, if you go to the Moon or if you go up to Mauna Kea, the G will decrease. Therefore, the weight will decrease. The weight, the apparent weight, I believe there is a section on your book about apparent weight. That's the one that you see on your scale as you jump on it. So this one may also change as well if you're being accelerated. But my pitch increased. You mean like that? Whoa! So if I talk very slow, is it back to normal? Oh, well, that's the problem. Because okay, obviously I have a problem on my end. Do you all have Henry's problem, or is it just Henry? That means, do we have to disconnect and reconnect, hoping that it will be fixed? Or should Henry disconnect and reconnect? Oh, Jamie's fine. Anybody else, please? Okay, Henry, I believe you may be on your end. We'll wait for you. Huh. Technology. Are you giving me a hint, Johnny Marr? Okay, I'll go slower. maybe you know, Mabel. Maybe sometimes it may not be the technology. Maybe I got a couple of fuse that burn in the middle of the session. Okay, welcome back, Henry. Is it better? Or are we going to call you Jeanne d'Arc? Okay, perfect. Okay, so we know the weight of A. They're giving us the coefficient of friction, both of them. Therefore, we know that there is friction between object A and the table. All right. First, we've been told that the weight hanging is chosen to be 12. Okay, so that's a little weight W. So weight is given to us. And the system is at equilibrium. Question is, find the friction exerted on block A. All right. So if we're looking for the friction on block A, then obviously, naturally, we want to go after A. And if we can get away with just this, we're good to go. So let's do a free body diagram on A. We're going to have its weight. Let's stick with W since we're being given W. The normal force. There's only one in this problem, so I keep N. The tension. And we're being told that there is friction between A and the table. Now, given the identified forces, what can possibly be the only direction or tendency of motion of object A under those forces? Excellent. Do everybody agree that based on the only force that are present that we have just identified before we get to the frictional force, if there is force between A and B, then obviously this force is horizontal. And if the only force in the horizontal direction is the force T that tends to pull A towards the right, then the friction must be towards the left. Do we all agree? All right. Perfect. Now, in addition to this, and Henry already pulled the cat out of the box, but what kind of friction are we dealing with? FK or FS? Yeah, thank you, Mabel. I was wondering the same thing. How come somehow Henry no? But let's clarify this. Yeah, excellent. The keyword equilibrium tells us that our system, that we can use FS to analyze our system. Good. Now remember, there is another question that we ask ourselves. If or when we know that we're dealing with FS, what is the next question? You have it on your notes, right? We did it last time. Yeah, can we consider FS max? Perfect. So what is the answer to that second question? Can we, in this particular problem? But only up to part A, right? I don't care about part B just yet. Again, Henry, I'm only reading up to part A. Is there... Cynthia says no. Yeah, okay. So remember, the second question is, can we use FS max? And for us to answer that question, we need to find the keyword min, max, or about to move. Those keywords are nowhere to be found because we're doing part A. Part B, that's a different story, but we're still on A. Hence, we know that we're dealing with Fs. We know that Fs is towards the left. And we know that we cannot use neither μs or μk. Fs, we can take any possible value, and in this case, he will take the value of the tension. Does that make sense to everybody? Does everybody understand why I cannot put μsn? That's the major thing. That's the common mistake. People just throw μsn in there. Boop. Micro's good. Everybody else? Nope. The only reason we can use μs is what? Anybody can answer Kyle. What is the only way that we can use μs? If it is max. Exactly. And it is only max, if and only if we see the keywords minimum, maximum, or about to move. That's it. That's the definition. So let's stick with our definition. Then life is easy. So it has nothing to do with the dynamics, but it's an excellent question. It's just a definition. Now, Mossman asks, if the force is being applied, you're referring to the force T, but the object remains motionless. Okay? Is there a follow-up to that question? So what are you asking? There is an N, right? There's already an N, there is a T. Could you rephrase your question, Mossman? I think I understand it, but I'm not sure if there is an answer to it. Wouldn't we have μs if the force is applied, but it's not enough to occur movement? Wouldn't we have μs if the force is applied, but it is not enough to occur movement? No. No. If a force is applied, but it's not strong enough to cause a motion, then we're still on that slope. Excellent points. So remember, this is our net force. In this case, object A, we don't care about N, we don't care about W. The only force along the possible direction of motion is T. So T is our net force in this case. If T is 1 Newton, then the frictional force is 1 Newton. If T happens to be 2 Newton, the frictional force is 2 Newton. If T is 3 Newton, then the Fs is 3 Newton. In all those possible values for T, 1, 2, 3, the system hasn't moved yet because that force is still too small, and hence Fs matches the value of the net force because we're on the ramp. Does that make sense? So therefore we cannot use μs because we can only use μs if we know we're here. Does that make sense, Mossman? Excellent. μs, we only need to stick with the definition to know whether we can use it or not. Min, max, about to move. That's it. Good. Alright, so obviously for us to solve for this problem, since we're looking for, what are we looking for? The friction force. If say I pick my coordinate system X here and Y here, then obviously I'm stuck, right? Because as I apply Newton's law, my free body diagram is complete, every direction is taken care of, and end up with T is equal to Fs and N is equal to W. This one is useless, just for good karma, and this one doesn't really help because I don't know the value of the tension. Now, to go back to your statement, Mossman, if the value of T happens to be this value, then Fs would happen to be mu Sn at this point. If the value of t happens to be bigger, so right here, then obviously the system will lose its equilibrium property. And the object A, boom, is going to fly towards the right. So we need to figure it out. We need to figure out what is the value of t. If the system tells us that we're equilibrium, we can safely assume that t is here. Otherwise, the problem is wrong. They goof somewhere. So you can always double check this. Once you know t, calculate mu Sn and ensure that t is less. If t is bigger, then this problem is badly phrased, and you can contest it and get 10 extra points. If it's equal, you can always contest it. But if it's less, then it makes sense. So let's double check. Let's go for t. How can we figure out t? What is the second stage? And this should remind yourself of another problem called, where are you? Called E6. You've all done E6 because we are on, where are we on? On F. So as you crank up problem E6, you should realize now that it's exactly the same problem, even easier. So what did you do in problem E6? Or how are you going to solve for t now? You obviously need another equation. What system can you consider to have another equation? Excellent. Excellent. And remember, we talked about this when we talked briefly about E6 and E7. You actually want to pick a system that includes the nut and W, so you don't have to do it twice. Perfect. Excellent. So as you consider the weight and the nut together, the free body diagram will be the weight, the tension along this rope, let's call it T prime, and then we realize, hey, Newton's third law, this is the same T. Oh, okay, wait. Ooh, I'm sorry, I missed that, Henry. Okay. Thank you. I was focused on my white screen. I missed that. Good. Yeah. We don't want to do this. No problem. But is it clear now? As we just did the free diagram on the system suggested by Tyson. Okay, perfect. All right. Let's pick a coordinate system. Let's pick the usual. Make our life easy, so that all the directions are easy. So we are going to have T prime cosine 45 is equal to T, and then T prime sine 45 is equal to W. Alright, so really, if we combine now this and this, we end up with Fs is equal to T prime cosine 45, and T prime is W cotangent 45. As we manipulate this equation. So now it's time to check. I forgot who, I think it was Mossman. Let's put numbers. What is W? 12. What is cotangent of 45? 1? Oh, thank you. So that means Fs is 12 Newton. This better be less than its maximum possible value, which is mu Sn. It has to be. Otherwise the problem is all messed up. Let's check. Mus is what? Mus is always the biggest one, so 0.6. So 6 divided by 10 times the normal force, and the normal force is WA, 60. This is 36. we're good. So it means that 36 is right here. And under those circumstances, or this situation, or this value of W, which is 12 Newton, then the frictional force happens to pick the same value. So guess what, Henry? You were right. But it was luck. It was only because the angle was 45. Excellent. So you had a great intuition. If you have the intuition, go for it. Just let me know, so that I understand why you went that way. So that if the answer is wrong, at least you can get perfect credits. Perfect. 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 Good. Okay, so we've just decided that if, or figure out that if W is equal to 12 Newton, then Fs is also 12 Newton at equilibrium. Good. Let's make some space on the board and let's look at part B. Oh, yo. Not that one. Not that one either. Okay. So part B. Now imagine that the weight of the hanging block is increased by a small increment. Alright, so let's think about this. Part A. How come Hey, how come I'm still white? I don't like being white. There. Up, up. So we saw that if W is equal to 12, Fs is equal to 12. They're telling us that we're going to keep increasing the value of W. Therefore, we're going to go that way. So a little bit more. And we expect a little bit more. Now we know that this angle is 45, right? So they're asking us, how much more weight can we put so that the system remains at equilibrium? So we want to increase the value of W all the way up to where we're about to move, right before. So, in other words, they're trying now to give us a hint. What is the maximum weight? Exactly. You got it. So here we see the keyword max. Therefore, we know for sure we're looking for Fs max. Therefore, for sure, we can use μSM. Okay? So the last sentence was the one that confirmed that we could use Fs max because of the keyword maximum. But as you can see, the second sentence should have led you to the same conclusion, even though until then you hadn't seen the keyword min, max, or about to move. But if we do understand how friction works, just by reading, imagine that the weight of the hanging block is increased by a small increment. How much more weight may we add to the hanging object so that the system remains at equilibrium? This is very clear that this also points to the situation where Fs is max. Okay. So in this class, I will always give you those keywords, min, max, or about to move. So it's no ambiguity. But as you can see here, I didn't have to add the last sentence. This will come back in C270 or C271. So they may try to trick you by the way it's worded, just to make sure that you draw a little diagram and understand what's going on. Okay, so really then the only thing that matters is this becomes μSN. That's the only change, right? The equations are all the same. T is equal to Fs is now equal to μSN, and N is equal to WA. for this, what was the equation we had? We had t prime sine 45 was equal to w, and then t prime cosine 45 was equal to mu Sn, which was our t. So, same equations, exactly the same equations, except our Fs now can be rewritten as mu Sn. And now we're solving for w. So that means we need to solve for t prime. So t prime is equal to mu s n divided by cosine 45. And we need n in there. T prime is equal to mu s, wa divided by cosine 45. Okay, now we can substitute here. W, which is really W max, is equal to T prime mu s wa times sine 45 divided by cosine 45, therefore tangent 45. Okay, let's put numbers. 0.6, 610 times 60, tangent of 45 is 1. 36. Do you remember what was mu Sn? It was also 36, wasn't it? Was it a different board? I forget. Or did I erase it? Oh, maybe I erased it. But I think there was an answer to Henry. When we calculated mu Sn, which was mu SWA, I believe we ended up with 36 as well. Look, same thing. So it all makes sense. It's all consistent with each other. So it's a very, very good problem. It's a good problem, simple, that forces us to really think about the behavior of the static friction and how it can move up the ramp based on the situation. Thank you. I think that was Brian. Thank you, Brian, for asking for this problem. It's a good problem. Sure. Anything else? F9. All right. I like F9. I really, really like F9. So we strongly suggest that once we are complete F9, you redo F9, but you incline the table. Hint, hint. So, I redo the same problem. I need a picture. Okay. They're giving us the weight of A, the weight of B, mu S, mu K. What do they want? They want F, which is horizontal, such that the system moves at a constant speed. Oh, sure. There you go. Oh, no, not that one. There you go. Screenshot. Or do you have any specific question?
I'm going to mute the TV because my class is online right now. Sorry. I don't care. I mean, I can't hear it right now, so it's fine. Oh. My mother shanked me with a knife.
Okay, I'm back. Is my connection okay? Can you all hear me? Oh, right, okay. Whew. Somehow I have to use the Wi-Fi. So, see how that goes. Okay, perfect. So, I'm sorry, where were we? Oh, number 9, right? We just went back to that screen for... I forgot who, sorry. Is it okay? Can we go back to the other screen? Whoever asked me to go back to this. It was okay? Ah, okay, okay. Oh, joiner. Ah, okay. Alright. So, what are the keywords here? Can you tell me what's important as you read the problem F9 carefully? Because remember, before we start analyzing a Newton's problem, we always need to know, are we using the first, the second, or the third law before you do anything else? So which law are we going to use and how are you going to know? Whoever asked for the problem should be the first one to answer, because obviously you have looked at this problem and think about it, so you know exactly what I'm asking. Come on, we're wasting too much time. What I'm asking is read the problem. You've all reading the problem, right? Otherwise, let's move on to something else. Ah, I need to scroll down. My bad. First, third. Yes, how? Yes. Thank you. Okay, so we're good to go. Constant speed, keyword, therefore, first law. More than one object, therefore, third law. Thank you, Cynthia. Thank you, Tyson. And thank you, Kay, for justification. We're looking for F. F is obviously on B, so let's start with B. Free body diagram on B. You tell me. And since it's a hard one, let's start with A. Let's please believe me that we're going to use both anyway. So let's start with A. Free body diagram on A. Can you give me the list of external forces in order as we pick A as our system? Weight, normal, T. All right, perfect. This must be the weight of A, because A is our system. Normal force, this is the normal force between A and B, and the tension. Okay. We're being told that A goes to the right and B goes to the left. Okay. Now, let's do the same thing with object B. Obviously, A is not going to be enough because we don't know what T is. Weight of A, normal force, tension, and force. All right, those are 4. Weight of B, first one, normal force, Okay. Wait. So normal force. Which one? Can you give me more information about that normal force? Imagine that you're B. NB. So we haven't used NB yet, K. Can you give me more information about who is NB? And what is the source? The source of NAB was the normal force from object B acting on A. The normal force is the force coming up from the table acting on B. Is that the one that you call NB, Mr. K? The normal force from the table acting on B? Okay, perfect. Therefore, this normal force has which direction? Up, down, left, or right? Alright, perfect. Excellent. So NB is the normal force from the table acting on B, while NAB on the free diagram of A was the normal force from object B acting on A. Okay. Can we move on to the next force? Tension? Well, what is the property of the normal force? When is there a normal force? Imagine your B. Are the only forces such as your weight, the normal force from the table, the force F and the tension are going to be the only one that you're going to feel if you're B? Yes, Tyson, thank you. Aren't you going to feel something from A? Yeah. If A wasn't there, I would agree with you. Weight, normal force from the table, that horizontal force F, and the tension in the back. But obviously, there is a dude on top of B. Us. We need to take that into account. Jamie says, is that equal to the weight? He may or may not be. All we know is that our object B is in contact with the table and with another system called A. So let's just stick with the definition of normal force, which is we never know its magnitude. Hence, let's not assume that it's equal to the weight of A, even though you're right, Jamie. Even though in this case you're right. Let's not make it a general case. Otherwise, since I mentioned before starting this problem that you should do the same problem with an inclined table, if we make that assumption right now and we keep that assumption later, we're going to shoot ourselves in the foot. But that's excellent. That was a good gut feeling. So if we only stick with the definition of the normal force and we identify the facts that F is in contact with the table, therefore there is a normal force from the table acting on B, that's NB. But B is also in contact with object A, and the surface between A and B is above A and also horizontal. As we apply the definition of a normal force, what must be its direction? So the force coming from A acting on B is up, or is it down? Okay, perfect. And do we know the magnitude of this force, or can we use another law to allow us to match it with free body angular of A? No, we just said, K, we don't want to use this, right? We just said we don't want to use this. But we're using Newton's third law, right? Because if we use this, weight of A, any other problem that you have in the test, that won't work, because it's only a very specific case. So remember, we can never, ever, ever associate the weight of a normal force from the beginning. Never, never do this. You're always going to hit a wall. We only know its definition, which is its direction. So let's stick with this. The magnitude of the normal force will come down naturally as we shake the tree of the system of equations. So let's just wait until we get there. But we know, because we said at the beginning of the problem, that we're going to use the first law and the third law. That's where the third law comes in, right? Because we're looking at the normal force between our two systems. Between our two systems. Between. Third law. And hence, this N is also equal to NAB. Does that make sense to everybody? Thank you, Kay. I love having the opportunity to make a point about the normal force because it's such a common mistake. So make sure you write that down on your notes. Never, ever assume this magnitude. Okay? But always use the third law if you see it. So without the negative sign, Michael, right? Unless you're writing the vector, same magnitude, opposite direction. Okay? Does everybody agree with, yeah, perfect, with this extra force NAB? What is it down, and why is it called NAB? And why it's not called weight of A? Everybody good? Perfect. And Kay, the other reason why you don't want to put weight of A is because, remember, this is object B. What did we say about weight? The weight showing up in a free parallelogram of a particular system can only be the weight of that system. So the weight of A should never show up in a free parallelogram of B. Never, ever, ever. So just from that perspective, we know we cannot put the weight of A. Okay? Even though, again, I apologize to you and Jimmy who have already seen it. In this particular case, as we're going to do the algebra, it will end up being the same. But that's just because it's a very easy case. Exactly. It's all about the system that we're picking. Perfect. And then the two others that was suggested, the tension and the force. And again, the tension, we realize as we follow the string, and we use Newton's third law and the property of the spring, the pulley, sorry, that this tension is the same as this tension. Same. Okay, good, good, good. Well, that's it. That seems to be a very easy problem, right? All the forces are vertical or horizontal. Oh, thank you. I was wondering. Oh, it's too simple. Okay, so let's go back to A and complete it. First, if we're dealing with Newton's first law, and I'm trying to trick you here, are we going to use mus, Fs, or Fk? Since we're using Newton's first law, are we going to use Fs or Fk? And again, I'm trying to mislead you. Fk. So, the reason why it's misleading, obviously, because I haven't seen the right answer. Oh yeah, I did, sorry. Is you should not use the law that you're going to use to ask yourself and identify the correct frictional force. Remember, the first law applies if you don't move and if you move. You just happen to have to move at a constant velocity. So the first law is not a good indicator to identify whether you're dealing with Fk or Fs. The question that you should ask yourself to identify whether you use Fs or Fk should include Newton. It should include the concept of motion. If you are moving, and it doesn't matter how, whether at constant velocity or non-constant velocity, you're using Fk. If you're not moving, you're using Fs. So are we all confident now that since our system is moving, happens to be at constant speed, who cares? Just that it's moving, then we have to use Fk. Jimmy as well? Because I don't see, okay, perfect. We haven't seen max, min, about to move, so it cannot be USM. Ah, okay, perfect. Yeah, reading the question is essential. We always have to dissect it sentence by sentence. Ah, excellent, excellent, excellent. Perfect. So we're going to use Fk. Next question that we ask ourselves once we know that we're using Fk is identify the direction of motion of our system. In which direction does system A move towards? Up, down, left, or right? Right. Therefore, Fk for object A must be going towards the left. Excellent. And here is the reason why I don't put Fk in my free body diagram, but I put directly, mu Kn. Is because, in this case, not so much of a problem, because there is only one normal force. So it's obviously mu K and AB. But it will become trickier at object B because there is two normal force. So in general, when you write the Fk functional form, always associate the N with respect to the normal force of that surface. This is a surface friction. So you're only concerned about involving the normal force that has something to do at that surface. In this case, this is the only one present. So this has to be the N that you're going to use. Let's ask ourselves the same question for object B. We're also going to use Fk, but now B is in contact with two surfaces. There's friction both between B and A and B and the table. So, excellent. Since the force is going left, which tends to move B towards the left, the friction got to be towards the right. Good. Let's start with the easiest one. Are we talking about the friction between B and the table? Okay. So the friction between B and the table is indeed going right. How are we going to call it? Mu K times which N? NB or NAB? If we're dealing with the friction between B and the table. Excellent. We have to include the normal force from the table. Those two are linked. Perfect. Now, similarly, start thinking about the direction of the frictional force between B and object A. In which direction is this frictional force towards? Right or left? If object B is going towards the left, obviously object A is going towards the right. What does it say about the direction of the frictional force between B and A? Imagine your object B, Tyson, and you go towards the left, and there is something on your back that goes towards your, let's say, your head first, so towards your butt. Is that frictional force going to feel like it's going down towards your legs, or in the same direction as your motion? Excellent. Do we all agree that the friction between A and B is still towards the right? Excellent. Is it clear? Because that's a little bit tricky to see. Imagine between B and the table. It was easy to identify the direction of frictional force because the table is static. So the relative motion of B with respect to the table, which doesn't move, is easy to identify. B goes left, therefore frictional is right, because the table doesn't move. We have to use the exact same analysis between B and A. Imagine that you're A, like the table, and you observe the direction of B with respect to you. If A goes towards the right, and you're stuck on A because you're the reference, where's the direction of B with respect to object A? Towards the left or towards the right? If you're on A and you watch B going, is B going towards the left or going to the right? Left, right? Therefore, the friction is opposite. So it's still right. Does that make sense? That's the one we just did, right? Exactly. Exactly, Jimmy. Okay? And this one must be UK NAB. So this is the tricky part. This frictional force on B is going right. On A is going left. It's the same force though. Newton's third law shows up again. Okay? So be careful about that. That's it, problem is done. Obviously, the rest is a piece of cake. Y, X, Y, X. All your forces are either along Y or along X. So there is no sine, no cosine. We can do it close eyes, two finger and nose. Okay? So the rest is just algebra. You're going to have this plus this minus that is equal to 0. This is equal to this plus this. This is equal to that. This is equal to that. Beef, boom, done. And you solve for whatever they ask you to solve for. F. So you're going to have 4 equations, 4 unknown. NB, NAB, T, and F. So get rid of this guy, this guy, this guy. It's a 4x4. Excellent. Thank you for asking this problem. It's a great problem. So now what I would like to ask you is to do this problem. Or that problem. But this one, we have to make some assumption. Same problem, same question. Let's imagine that as F, or better, put F here, on A. Get F, such that the system moves at constant velocity, given that MB is bigger than MA. And introduce an angle alpha. Redo this problem with that new piece of information, and the fact that F is on A. Please work it out. Get a solution and send it to me via email or take a picture so that I can check it for you. Very, very important problem. Okay? Yep. Yep. Exactly. So same as F9, except F is now on A, but it's still along the inclined plane, the table, and the table has been lifted by alpha. And just make sure that MB is bigger than MA, because otherwise, physically, that may be weird. Exactly. You're just going to be carrying a couple of sine and cosine. But as you do this problem, okay, this is where you're going to realize, with confirmation, that this is no longer the same as this, while it is here. So that's why if we took the habit of putting WA here without the NAB, as soon as you put an angle, we'd be toast. So you're going to see how those two are not going to be the same if you have an inclined plane, as we've seen with inclined plane problem. So that will confirm to yourself, yes. Let's not make the assumption that I know the magnitude of the number of force when I start a problem. Let's keep it for the equations to give it to us. Perfect. Questions? Oh, I'm going overboard. Oh, well done, I'm running late. That's okay. Let's take a quick break. Let me release the board. And then, well, we'll do circular motion or we'll do a quiz after the short break. Now explain how the world knows how and when to apply normal force. I can't. That is not part of science. That is an excellent question, but it doesn't fall within the realm of science. It does fall within the limit of quantum mechanics, and I'm really hoping that you're all going to take Physics 274 to get a taste of it, or at least sit in that class. But you're going to have the same type of questions. Yes, yes, yes. Remember, when we have embarrassing questions like this in science, then we start asking ourselves, is the answer to that question going to improve our ability to come up with model that can explain observables or physical reality? If the answer is yes, then we burn some neurons. But if the answer is no, then we go, who cares? Let's give that question to philosophers or religious people, and they come up with an answer. So as far as we're concerned here with Newton, it doesn't actually really matter what the answer is, because we take Newton as a model, just a game, a bunch of rules, and he happens to predict very, very precisely what we can observe. But as you're going to take quantum mechanics, you're going to see that those questions in that particular context will become very, very important, because it will be the basis of observation, which mathematically is going to be this. That's how mathematically quantum mechanics represents observing. And this influence or implies the fact that the observer, you, is connected with the observed quantity. Which, go back to Jamie's question, oh, it appears that the two are connected somehow. Like, the normal force knows how much we pushed, so it can apply the exact same magnitude. Very, yeah, well, I wouldn't say creepy, but I would say interesting. So it's pointless but necessary for calculating things. You mean the normal force, or the answer to that question? Okay. Is there any time, Henry, that I could come in to look at this that is not in your office hours? Yeah, of course. Like I said many times. Email me, tell me when you can come, and I'll be there. Somebody, I forgot, Schussman, I think. Michael, yes, is coming tomorrow afternoon. So, if it's better for you, come tomorrow afternoon. I have a break between 4:30 and 5:30. I'm gone all day Friday, unfortunately. But if you cannot make it tomorrow and you can only come on Friday, then I will give it to one of our co-worker, and you can pick it up from her. So just let me know. Yes, Busman, Schrodinger's cats. It has something to do with this. Yeah, observation. Absolutely. No, I have meeting between 1 and 4:30. But if it's just to pick it up, yes. You can just wave, and I can just, slide the test to you during my meeting in my office. No problem. But in case you want to sit down and, compare, if you look at the solution, you realize, okay, I don't understand what's going on here, then you want to come back later. But if it's just to pick it up, sure. Just wave, say your name, interrupt my meeting, no worries. I'll be in my office. Yes, tomorrow. Yeah. I'll be here from 1 to 4:30. Sure. Perfect. Okay, let's take a quick break. 6:13. I talked too much.